Good morning, good afternoon, good evening, ladies and gentlemen. Welcome to today's webinar by Solarplaza. I'm happy to have you all here. It's really good to see that we have people from all over the world, even Japan, Australia, Africa, Europe, and obviously North America and South America. Our webinar today is on PID. Brief agenda. First, a short introduction by me. After that, Jenya Meydbray from DNVGL will talk about model degradation results across multiple stress tests and PID. Afterwards, Adrián Ramos from Omron will present the actual case study on PID, and will be plenty of time for Q&A afterwards. My name is Eelco Hoogtuin. I'm a project manager at Solarplaza. I work on the solar asset management conferences in Europe and in North America. My background is in rooftop solar. These are my contact details, so feel free to get in touch with me if you have any questions on solar asset management or one of our conferences. For those of you who don't know Solarplaza that well, we started the company in 2004 already. Since then, over 80 events have been organized. We mainly focus on trade missions in emerging markets and conferences in the more mature markets. We work on a global level all over the world, and we currently have a network of over 50,000 solar PV professionals. This webinar we provide you today is in preparation of our Solar Asset Management North America conference coming up on March 28 and 29 in San Francisco. There will actually be a site visit on the day after the conference, so total duration will be 3 days. This is the leading conference focused on the operational phase of solar plants and portfolios. It's already the 4th edition. We expect 500 attendees plus this year, over 70 leading experts on stage as being a panelist or speaker. We have over 40 sponsors and exhibitors at the show, including the presenters of today. And you can already find the program online at solarassetmanagement.us. These are the sponsors, and I would like to say thank you to them for making all these conferences and webinars and all the other content we provide on our website possible. And this is a list of confirmed attendees for the conference in March. We expect this list to grow obviously in the coming weeks, and we are looking forward to have you here as well. We provide a discount code today as for all the webinar attendees. So if you use webinar 20 as a discount code on the website, the first 20 conference tickets will get 10% off. I will show this slide again after the webinar, so please don't leave the webinar. So practicalities for this webinar: if you have any technical issues, please use the chat box we have. For Q&A, you can also use the chat box. We will address as many questions as we can after the webinar. Total duration will be approximately 1 hour. The presentation, the slides, and the video recordings will be available at the website solarassetmanagement.us. So feel free to share them with your colleagues afterwards. We prepared one poll question today for on PID. Let me bring that up. So I would invite you all to vote on this poll. We are curious to see whether you have experience with PID in your business, in your plants. So please select one of the following options. Yes, I am currently facing it. Yes, we have dealt with it in the past. No, but I would like to know more about it to make sure I'm able to mitigate risk. Or no, PID does not bother me. I will wait a couple of seconds for everybody to vote. I'm happy to see many people are voting. So these are the results, and we see 50% of the audience would like to know more about PID. Well, it doesn't exclude the first two answers. Anyway, not many people that are here that are not bothered by PID. So I guess you are in the right place, and we are organizing the right webinar for you guys. Very interesting result, and I think this provides a basis for the presentations we are about to see. So first speaker of today will be Jenya Meydbray. He's Vice President Strategy and Business Development at DNV Laboratory Services. He's a member of the NRO Advisory Board on Module Quality Assurance Task Force, and he's a member of the Board of Directors of PV Complete. Jenya, I'm about to make you a presenter. So please be ready to share your screen.
Very good, thanks.
Please go ahead.
Okay, well thanks Ilko, and thanks to Solarplaza, and thanks everyone for coming today. My name is Jenya, I'm with DNVGL as Ilko mentioned, and we'll talk about PV equipment diligence best practices here today. So quick little commercial on DNV for starters. DNVGL is the world's largest renewables advisory firm. Over 2,500 individuals in the energy group, and over 1,000 of those are focused on renewables. There are 27 offices worldwide that focus on solar, largest being in the US and in Europe, and have advised on over 5,500 solar projects. So quite a large organization. So I'm with the laboratory services side of the organization, which is different than the independent engineering side of the organization. So independent engineers are regularly engaged by financial institutions, investors, developers to provide an expert third-party opinion on technical risks. So the selection of the equipment used in the plant is critical to the risks. And I'm on the, as I mentioned, laboratory side of the house. We perform the testing on the PV modules, PV inverters, and battery systems. Independent engineers, in the absence of data, can only draw conclusions based on broad industry averages and historical precedent, but ultimately independent engineers are data-driven. So the data that we generate should feed into the independent engineering process and should benefit your projects almost all the time, assuming the data reflects positively on the equipment that you are planning to deploy. So this chart here shows degradation rate on a % per year basis of PV modules and systems as compiled by NREL. NREL is the National Renewable Energy Lab in the US, based in Colorado. They performed a giant literature survey and pulled out the degradation rates that people were seeing. The median is 0.5% per year, which is great. That's kind of what everybody would like to see. The average is 0.8% per year, a little bit worse, but still within a reasonable number. I think the real conclusion, the real takeaway from this is the very long tail. There is a lot of degradation rates that are observed to the right of 1% per year. And the P90, meaning 90% of the systems are at this or better, is 1.3% per year, meaning 10% of the systems are worse than 1.3% per year. This is not a very good number. I think most developers would not be very happy. Most system owners, IPPs, would not be very happy if their systems were degrading at 1.3% per year. We think this is driven primarily through equipment quality issues, things like PID. So this is a cartoon pulled from the IEA, International Energy Agency publication. You can Google this reference up at the top and you can get the full paper, but it basically shows the different mechanisms that lead to PV module aging and degradation. So in the early phase, I would say within months or first few years of deployment, infant mortality is driven by a few issues. String interconnect is one that you'll see repeated across the area, and that's supported by our observations in the laboratory. We see a lot of string interconnect issues, basically cell-to-cell interconnect or busbar-to-busbar interconnect inside of the PV module, solder joint degradation. PID will typically cause either infant mortality or midlife failure and will cause severe degradation, and then there's the long-term degradation, the loss of output of a PV module caused by the yellowing of the different materials and again, the cell interconnect, the degradation of the solder joints that hold the circuit together. One important thing to keep in mind is that the vast majority of the solar out there today has been installed pretty recently. So this chart is from GTM Research. The 85% of the deployed capacity as of 2015 was just installed in the last 5 years. So we have a long 20, 25-year service life expectation. We don't know what the 20, 25-year performance really looks like for today's products. There are very few systems that have been out there for 20, 25 years. One way to obtain valuable information about the long-term reliability and performance of PV modules is through accelerated laboratory testing. It's really the only way to obtain a view on really long-term performance today in a commercially reasonable time frame. Of course, the best test would be to deploy the equipment and wait for 25 years and then see how it works at the end of it, but obviously that's not reasonable. So where can the DNVGL Laboratory Services Group help in the project development process? So I'll repeat again that this is just where the Laboratory Services Group can fit into the development process. The independent engineering side of the house has a lot of additional services that apply in the solar industry in addition to these services, but ranges from lab testing to field testing to factory audits to resource measurement. And we work with our clients from the planning phase all the way to the asset operation and M&A phase, assets changing hands basically. I'll talk a little bit about the product qualification program today, but I won't get into the details of most of these other things. Anybody can feel free to contact me for additional details on any of these items. So the component testing services that we focus on is the product qualification program, statistical batch testing, and field testing. The product qualification program is kind of the bread and butter service that we've built the business on. This is where we have defined a very robust, rigorous program testing PV modules, PV inverters, and batteries and energy storage systems. We execute the same testing program on every manufacturer. We have the vast majority of manufacturers now participating in the program. I think it's 75% of the manufacturers on the Bloomberg Tier 1 list are participating in the program. The testing is done per bill of materials, which is absolutely critical. Different modules can have the same model number, model name, but different bill of materials. So it's important to test across those. I won't get into the details of all the different testing here, but you can see it outlined here. We have downstream partners, which are developers and banks primarily, and IPPs that can obtain these results at no cost. So if anybody on the buy side of the solar industry listening today, feel free to contact me. You can get engaged in this program and we can start sharing reports with you at no cost. And the idea is this helps you with vendor selection. Once a vendor is selected, the risk then shifts from product design and bill of materials to that more of the ability of that manufacturing facility to consistently produce that product 100,000 times or however many units you're buying. And then we go into a statistical batch testing. So this is where we sample a statistically significant number of modules from that batch, from the batch that's actually being shipped to your product, and subject it to some shorter but larger volume testing to ensure that there are no exposure to manufacturing quality issues or serial defects. Finally, once the plant is installed, we shift to field testing, and this is thermal imaging from an airplane, from a drone, electroluminescence imaging in the field, things like that. Typically for acceptance testing or a diagnostic testing if you think that something may be going wrong. This is a little cartoon that shows how the product qualification program works. On one side of the table we have manufacturers. Manufacturers pay for the testing, we engage with them. They're the ones we contract with. We have downstream partners. We sign engagement letters and NDAs with and we share reports with at no cost. And we kind of sit in between the downstream partners and the manufacturers. So we can help the downstream partners with selecting who to invite to an RFP or even helping go through the RFP process. We can help manufacturers that perform well in the testing programs get in front of the right downstream partners, the right developers and banks. We use the data from our qualification program to publish this, what we call the PV Module Reliability Scorecard Report. It's a totally free download, available on dnvgl.com. We've released 2 versions so far. The 2017 version will be coming out this year. It contains high-level test results compared manufacturer by manufacturer, and it names names. So it names which manufacturers are performing well. In 2017, for the first time, we'll be releasing an inverter qualification scorecard. So this is going to be a new report for us in 2017. Over time, we hope to also release one for battery storage systems. So some of the results in this PV module reliability scorecard look like this. This is the type of data that's in there. Thermal cycling is one critical test that's performed. PV modules are put into environmental chambers, which is basically a large stainless steel box with very heavy-duty heating and cooling systems in it. The PV modules are heated between 85 degrees Celsius and cooled to negative 40 degrees Celsius and then cycled back and forth 600 times for this test. So after 600 cycles, the difference in the coefficient of thermal expansion of the glass and the silicon and the metal and the polymers causes the solder joints to get stressed. So when we see the solder joints getting stressed, we see cracks initiating and propagating through those solder joints that degrade that cell interconnect that you saw earlier. Some modules perform very well, so this green line indicates all the ones to the left are named in alphabetical order here. On the right, those are all anonymous. Those are the ones that are performing not as good. Damp heat, this is a just very hot, humid, steady state test. So it's 85 degrees Celsius, 85% relative humidity, and you just keep it at that for 2,000 hours. That's about 85 days or so. Again, to the left in alphabetical order, you see which manufacturers have degraded the least. The percentage here shows the relative degradation of power output from before the test to after the test. Finally, the topic of this webinar is PID. We do PID on a lot of manufacturers. As you can see clearly from this chart, some manufacturers do quite well and degrade almost not at all, and others degrade very severely. About 40% of the modules tested degrade more than 5%. So that would be to the right of this green bar, and those are obviously anonymous. The conditions in this test outline here is negative 1,000 volts for 100 hours under the damp heat conditions. That's the 85-85. The high temperature and the high humidity is kind of a worst case scenario for PID to happen. So quite a bit of modules that are commercially out there today still suffer from this issue. So what is PID? So this is a little cartoon that kind of demonstrates what conditions cause potential induced degradation. The potential in question here is voltage potential. So inside of a PV module, you have 60 or 72 solar cells that are all wired together. Each solar cell adds about 0.6 volts, and you wire it up in series up until 600 or 1,000 or soon to be 1,500 volts at the string level, and then you put a bunch of those strings in parallel. At the end of that string, you have the cell at 1,000 volts, and you have the frame at equipment ground. So the frame is a piece of metal that's bolted to the rack. Typically that equipment is grounded. And so you have a fairly large voltage potential between the cell and the frame. That causes an electric field over that area that goes over the glass, and sodium ions in the glass can drift either towards the cell or towards the air, either inside of the panel or outside of the panel, depending on the polarity of that electric field. So the green line shows if you have the negative pole of your PV module string grounded. So then the negative side of your electrical PV module string is actually at the same potential as the equipment. So the only voltage between the cell and the frame is going to be positive. So the cell is going to be at a higher voltage potential than the frame always. First module will be a little bit higher, last module will be 1,000 volts higher. Or in the case of a 1,500 volt system, it'll be even 1,500 volts higher. In this scenario, you do not suffer from PID. The risk of PID doesn't exist because the sodium ions are simply pulled towards the air. They're pulled away from the cell. In the event that this green ground doesn't exist and your system is floating, electrically floating, typically one side of the electrical string is negative. The cells are negative relative to the frame. The other side, they're positive relative to the frame. In that negative side, that's where the sodium starts to get driven towards the cell. And this is the scenario where you can have PID degradation. So PID is just a little bit more on it. It's one of the primary technical risks causing early lifetime PV module degradation. And it could be quite severe, as you saw earlier. It can be 20+% down. And it's typically just one side of the string because only one side of the string has the voltage potential. The higher the voltage potential, the higher the risk. So you also then have the added effect of increased mismatch. So the modules are all in series. You now have a lot of mismatch module to module. It's important to note, though, that not all modules are sensitive to PID. If we do these tests, we can demonstrate which are sensitive and which are not sensitive. So the little cartoon, the little drawing here of the PV module kind of shows the frame that's metal and grounded relative to the cell. It's the potential between these two lines that drives this sodium ion drift. Okay, thanks everyone. That's all I had.
Thank you, Jenya. We have a couple of questions coming in, but we will address them after the webinar or after the presentation of Adrián. So thank you very much, Jenya. Very interesting. And yeah, we'll get back to you in a bit after Adrián's presentation.
Sounds great.
Next speaker is Adrián Ramos. He's Senior Business Developer in the Environmental Solutions business at Omron. He's responsible for the new business strategy development and product innovation with a strong focus on the North American inverter market. Adrián has an extensive background, we can say, in the downstream photovoltaic industry. He's been working on the design of PV systems, formerly technical due diligence and on-site technical audits. Adrián, I unmuted you and I'm about to share your screen, so please go ahead.
Okay. Yep. So here we are. First of all, well, this is Adrián Ramos. Thanks to everyone for joining us today. As you can suspect, this webinar is focused on PID and its dramatic consequence when it is not mitigated. In particular, I'm going to cover today in my presentation the understanding of the PID effect. This is kind of overlap with Jenya, but I think that it's going to be instructive as well. The PID identification and mitigation, as well as some actual cases of PID. Finally, I will introduce the Omron solutions to prevent and recover the PID issue. Feel free to write down your questions, since we'll have a Q&A at the end, and we can discuss further on. So, first of all, I would like to have a word about Omron, given that we are a newcomer in the US inverter vendor space, and most of you might not be aware of us yet. So, Omron is a highly diversified Japanese technology group, which is listed at the NASDAQ, and has been included as one of the top 2,000 largest world companies by Forbes. With reference to the PV sector, Omron ranks as the top global single-phase inverter manufacturer over the last 3 years, thanks to its strength in Japan and EMEA, deploying an excess of 6.5 gigawatt of single-phase string inverters. Beyond that, Omron employs more than 36,000 people and has over 200 branches in the world. For what respect the US, we've been in the country for the last 25 years, and our headquarters are located in Illinois, I would like to also to mention that we have recently acquired 2 companies focused on robots in California. They are Omron and Delta Tau. Since a picture is worth more than 1,000 words, let me introduce you the kind of products that we manufacture. The first you can see here up on the left is a blood pressure monitor. Then you have a programmable logic controller. You can also see here a PID preventive PV inverter and a relay. At the bottom left you may find a 6-axis robot alongside our an autonomous indoor vehicle, both manufactured by Omron, which is based out San Ramon in the Bay Area. And well, just for you to know, this autonomous indoor vehicle is currently being used at Tesla's Gigafactory. Yeah. So PID, I think that Jenya covered this part, but let's come back again for a second. So PID stands for potential induced degradation, and it's a phenomenon that may produce power degradation in the PV models. But how does the mechanism work? In this slide, I'm illustrating a regular configuration of a given PV string comprised of 8 modules, which are connected in series to a transformer-less string inverter. As you can see, the module frames are grounded. The first of 4 modules on the left are connected to the negative string pole and present a negative potential in respect to the ground, whereas the 4 modules connected to the positive pole present a positive potential to the ground. You can now appreciate the profile of a PV module. You might find the frame, the PV cell, and the glass. So let's detail the grounds of a PID effect in just 5 steps. First of all, and according to the regulation in many countries, such as the US, the module frames are required to be grounded. Second, there is a voltage difference between the module frames, which are grounded, and the PV cell across the negative pole of a string. Third, the voltage may cause a migration of ions within the module. Fourth, positive sodium ions contained in the glass can migrate towards a PV cell. And fifth, crystalline defects in the PV cell permit the ingression of these sodium ions resulting in module degradation. So here you have an easy way to understand the PID effect, which is a little bit complicated from a technical standpoint. Once again, if you have a module frames to the ground, the PV module glass is made of sodium, and there is a negative bias between the PV cells and the frames. We may have a migration of sodium ions from the glass to the cells that result in the module degradation in the negative pole. As already detailed on Jenya's introduction, PID effect on PV models depends on the bill of materials, manufacturing process, and environmental factors. It is important to note, though, that the effect of PID is aggravated as time goes by. You might see at the PID test charts that the absolute value of the module power loss increases the longer the models are tested. It is also significant the high number of PID cases reported in Europe, since, as you might know, transformer-less inverters have been more popular in Europe than in the US. However, recent code updates have allowed for ungrounded system in the US as well. In particular, the first transformer-less inverter was available in the US in 2007. From that point onwards, the PV industry has seen an increasing adoption of transformer-less inverters, solutions that could develop PID on modules. This reality connects with the little to known PID footprint in the US, since most of the inverter topologies were grounded thanks to the transformers in the near past. Now that the PID effect has been explained, I would like to focus on the economic impact of PID. And for doing so, I will summarize some of the data reported by the research group Solar Bankability. Solar Bankability is a consortium of European research groups funded by the European Commission that has analyzed an operational 772 plant 450 megawatt PV portfolio to understand what are the actual risks of PV models and their economic impact. In such a way, Solar Bankability has defined the cost primary number, which is the sum of the costs due to downtime plus the costs due to fixing the failure for a number of model issues. In terms of a cost parameter number, the most significant failure for PD models turns out to be glass breakage, followed by PID. In particular, it is reported that PID has a 5% failure rate over all technical failures and a cost parameter number of €6 per kilowatt peak per year. Accounting for a 20-year planned lifespan, that is an economic impact of 12 euro cents per watt peak due to PID over the entire portfolio. So 12 euro cents per watt peak is the cost of non-preventive PID according to this research. Let's turn now on the identification of PID. The most remarkable.
Sorry to interrupt. Can you move your microphone slightly away from your mouth?
Okay. Yeah. Better now?
I think it's much better now. Thank you.
Okay. Good. So talking about the identification of PID. The most remarkable fact when identifying PID is that PID is not visible to the naked eye. The most used techniques to detect the PID on modules are the EV curves of the modules, electroluminescence images, and thermal images. It is good to know that if detected early on, PID might be reversible. So how can we mitigate the PID? Well, there are mainly two ways to do that, to mitigate the PID. One is the prevention, which is the one that we recommend. And you can also go for recovery. As for prevention, I point out two options. One is a PID lab test for a batch of models before the installation, and I'm sure that DMVGL will be happy to support you with that. And the second is Omron inverter topology that I will explain later on. As for recovery, there are also two options. The first one is to ground the negative pole of the inverter, and unfortunately this option is not possible in many of the cases. In addition to that, it depends on the inverter vendor to complete a warranty for a new configuration. The second recovery option is to install a PID recovery box. So let's touch base on the Omron PID preventive topology. 10 years ago, Omron made the decision to develop a multi-level string inverter topology that worked with a DC negative pole connected to the ground. Back then, the ambition of our R&D team with this topology was to reduce the delamination effect on thin film modules. Later on, we discovered that by grounding the negative pole, that the threat of PID was prevented, enabling low-cost, high-yield PV installations. We made this innovation real with the KP100L, which is a three-phase 10 kilowatt inverter that has been deployed in EMEA. So far, we have shipped more than 10,000 pieces of these machines, surpassing the 100 megawatt deployed. Once again, we have the model grounded, the PV module glass made of sodium, with the difference that now the negative pole of the string is connected to the ground. Therefore, the potential induced degradation, or PID, is prevented by using the Omron transformerless inverter topology. We used to say here that let's keep positive. Let's talk now about the PID recovery box for retrofit purposes. The only function of the PID box is to reverse the polarization effect on the PV cells affected by PID. The PID box makes this happen by applying little currents to the modules overnight that bring the sodium ions back from the cells to the glass. During the day, the PID box is off and causes no effect to the normal functioning of the string. It is important to know that this method to recover PID-affected modules has been tested, is plug and play, and is compatible with different string sizes and all the inverters. So now, I would like to introduce an actual case of PID where both the PID recovery box and the Omron inverter topology were used. The site was located at the south of Italy and built and operated by Juvi Solar, which is a large solar EPC and developer worldwide. A few months after the commissioning of the PV site, the performance ratio decreased below 60%. The plant kept the performance ratio during several months, but however, immediate action was required to recover the plant and pass the final acceptance certification. Eventually, Dewey contacted Omron, so that the 1st of April, the inverter was replaced and the PID recovery box installed. After just a week, the performance ratio recovered, reaching values of almost 75%. Later on, Dewey managed to pass the final acceptance certification and reverse the PID effect on site. Therefore, as a conclusion, we might say that potential induced degradation, or PID, is a real phenomenon that reduces the performance of the PV model. The economic impact of PID has been reported to cost 12 eurocents per watt peak. Negative PV bias is required to develop PID. Omron's patented transformers inverter topology prevents PID by connecting the negative DC pole to the ground. And finally, Omron PID box mitigates PID in operational PV plants without the need to replace the modules. As a final comment, I would like to mention that we'll be at the Solar Asset Management North America in San Francisco next March, and we'll be glad to introduce our products to you there. Feel free to get in touch, and thank you very much for attending the webinar. Alco.
Thank you, Adrián.
Mm-hmm.
Please stay on the line for some Q&A. We actually recommend that same Solar Asset Management Conference as well. Might not come as a surprise. Yeah, some further reads before we go to the Q&A. As Jenya mentioned, there's this PV module reliability scorecard report. If you Google that, you'll probably find it, or I'm pretty sure you will find it. As Adrián mentioned, there's the Solar Bankability group, solarbankability.eu. There's quite some extensive reports there as well. So let's go to the Q&A. Jenya, first two questions to you, just to verify the, let me unmute you. The damp heat test, is it correct that 2,000 hours?
Yeah, so the damp heat test as outlined in the IEC certification is 1,000 hours. The scorecard, the purpose of the scorecard is to provide reliability testing that's a much higher bar than the minimum kind of certification standards. So we are doing twice the duration for the damp heat test. For thermal cycling, we go out to 600 cycles, which is 3 times what's required in the IEC. And then we do some other tests. PID, for example, is not even part of the IEC certification. Dynamic mechanical load, also not part of it. So that's right. So it's beyond the IEC requirements.
I see. And then there's another question. Is the PID test at DNV, GL, PVEL 100 hours or 1,000 hours?
100.
Okay, clear.
So that's right. So what was presented there is 100 hours. We typically do up to 200 hours just to get another data point. So, but typically what we see in PID is a module will either degrade right away or will be pretty solid. That's typical.
Okay.
It's typically really an early lifetime thing.
Okay. Adrián, question to you. Can Omron provide details on what the PID box actually does? Does it reverse voltage at night? What voltage? What time is there? Is it test data showing it works on any module type? Yeah, feel free to answer, but obviously if there's any confidential things, don't mention those. But.
Yeah. Well, there's no problem, you know, sharing the information that we have. The model manufacturers are not a problem most of the time, because they are the first interested in, you know, healing the panel without the need to replace it. Most of the time the problems with the PID recovery box are coming from the inverter manufacturer, because since you are you know, injecting some currents, if you don't open the circuit to the inverter, you can have some issues in the inverter. So depending on the configuration that you are choosing for the PID recovery box, you should need kind of permission for you to do so, right? mainly what the PID recovery box is doing is just introducing some little currents. So you increase the voltage overnight. There is a DC boost in the PID recovery box, and this voltage is applied to the modules in order to reverse the process. So let's say that if during the day the sodium ions are going from the glass to the cell, overnight what you are doing is applying a different potential in order to bring back those sodium ions from the cell to the frame. Yeah, that's it.
Okay. Okay. Another question to you, Adrián. We see you have quite some competition on anti-PID measures. How do you compare to them?
You mean the technology of the modules, like N-type modules?
Yeah, we see quite some technologies popping up in the market, anti-PID, either with a box or not sure about inverters, but yeah, there's a couple of companies out there, I think. And how do you compare to them?
Yeah, but I don't get your question. I mean, are you referring to the PID recovery box or
yes, exactly.
Yeah.
The anti-PID box, is it very different than the one from your competitors?
Okay, I understand your question now. Yeah, well, the difference between our competitors is that we are providing, Omron warranty. So this is not kind of, a startup offering, let's say a 2 years warranty on a product that you don't know what's going to happen with it. Mm-hmm. You have the shoulder of Omron, and we are going to stay there in the future. The second thing is that there are some companies offering only one solution that I think that is the parallel solution, which most of the times require the warranty approval from the inverter manufacturer. And we are providing either the parallel solution and the series solution for the PID box.
I see. Thank you. So, question to Jenya. What kind of standards do you follow when you do PID test?
Sure. So the conditions in the environment in the chamber is damp heat. So it's 85 degrees Celsius, 85% relative humidity, and negative 1,000 volts is applied between the cells and the frame. So this is, yeah, those are the conditions outlined. The IEC, there is an IEC test standard that was, or test procedure that was released recently that outlines a couple of options. That's one of them. There's a more mild PID test that's also outlined. It's the same thing basically, but at 60 degrees Celsius. So,
okay.
The one we use is 80. The one we use is 85.
Okay. Is there a relation between PID and snail tracks that you are aware of?
So no, the snail trails are cell cracks. So basically, the EVA encapsulant gets discolored by the moisture and oxygen that gets through the cell crack in the silicon, and the moisture and oxygen get through the crack and discolor the encapsulant slightly, so you can visually see the cell cracks. The cell, if you were to image that module with an electroluminescence imaging camera, you would see that there are cell cracks in the location where there are snail trails.
Okay. Adrián, another question to you. There's a question about the warranties that you guys provide on the inverters. Mm-hmm. So with the PID box, do you how does that relate to the inverter guarantee? Can you completely, yeah, or maybe you can elaborate just a bit more on the warranties on these and what kind of guarantees you can give on the anti-PID?
Yeah. Okay, so first of all, this relates to the inverter that you have already installed, right? So it is not our inverter; it's someone else's inverter, right? So since you are, let's say, changing the system configuration that you have because you have an issue, right? You have an issue at the string level, and you are including a box that is injecting some currents at the string level. You need to double check what are you doing, because you can destroy or you can damage your inverter, right? So that's my point, that the PID recovery box is a solution, but you need to do a technical assessment on the configuration that you are going to go for. And sometimes, since you are, matching, or let's say including the PID box where the inverter is connected, you need to double check with your current inverter manufacturer if they are going to keep the warranty of the inverter if you install that PID recovery box with a given configuration.
Okay. Another question on the PID box: are the devices connected in series between the inverter and the modules?
That's one of the cases. You can connect the PID, once again, the PID box can be connected in series or in parallel, and series is one of the cases. Yeah.
And another question that comes in: do you keep them there for a long time, or do you remove them once the modules are recovered?
Yeah, that's a very good question, and that's why we go for prevention, right? The problem with the PID is that once it appears, you can only recover the modules, but if you remove the box, you're going to have a PID again, because it has showed up already. So that's a point. If you don't go for the hard grounding or use our unique Omron inverter topology, you need to keep the boxes or change the models.
Mm-hmm. Yeah, I think that answers the question pretty well. Jenya, another couple of questions for you. Yeah, as you mentioned, a lot of testing is BOM, bill of material specific. So the scorecards are basically modules or brand specific. How does it relate to each other?
Yes. So the scorecard is intended as a high-level summary of test results that is free and available without restriction. We have very detailed test results per bill of materials available that those high-level results come from. In order to obtain those, you need to be part of our downstream partner network. So for that, you just contact me, sign up. There's no cost involved, and then we can start sharing reports with you. It gets back to our the kind of diagram I put up of how we sit between the manufacturers and the downstream partners. The manufacturers sign waivers after the tests are completed that grants us permission to share under NDA with our downstream partners. So to the extent that we have the permission to share, we're happy to do so and happy to support our downstream partners in vendor selection for projects.
I see. Then there's quite a few questions coming in on different types of modules. As far as I saw, it was only crystalline modules out there. So maybe there's something you can tell us about double glass layer modules. Not sure if I pronounced it the right way in English. Thin film. What does that look like?
Sure. So I'll start with the double glass. So glass modules are basically, so standard module construction is a glass on the front, the cells inside, and then a back sheet, typically made from Tedlar or some polymer material, a back sheet on the backside. The glass modules replace that back sheet, polymer back sheet, and put another piece of glass there. There's a piece of glass in front of the cells and behind the cells. So it's like a sandwich, glass sandwich. How does that relate to PID? So for PID, you need a something metal that acts as your electrical ground plane. So for standard modules, you have a metal frame that acts as your metal ground plane. For glass modules, you typically have no module frame, so they're typically frameless laminates, but they do have metal clips, typically 4 metal clips along the 2 on each side of the long side of the module. So those act as the ground plane just as the frame does. So the cells affected by the PID stress are the ones that are physically close to those metal clips rather than around the entire perimeter of the module. So PID is still a concern. Thin film is a totally different mechanism. So the sodium can impact cadmium telluride or CIGS, or we don't see too much amorphous silicon anymore, but that mostly CIGS and cadmium telluride can be impacted by that type of stress as well. The physical mechanism is different. It's not a sodium-driven degradation of the PN junction per se, but nevertheless, to the system owner, it doesn't matter. Degradation is degradation. So the test is still relevant for thin film modules. There are some degradation mechanisms that can happen. So were there any other specific module technologies asked about, or that's
no, I don't think so. I think that covers it. Yeah, the questions keep coming in, and I think that's always a very good thing. That's what we're aiming for at the conference as well, make it as interactive as possible with panel sessions and a lot of audience interaction. So I think it's great. Mr. Ramos, yeah, we have quite a diverse list of attendees here for this webinar. We have a lot of people from the UK, I saw. Obviously a lot of people in the US, the European continent. So there's a couple of questions about negative grounding of inverters. Can you elaborate a little bit on that, what the differences are among the continents, and how does it obviously relate to PID?
Well, that's I think that you can write a PhD on that, but I would go for a technology differentiation, and this is something important. Nowadays, we are seeing that three-phase string inverters are having a rapid growth, not only in the US or the UK, but in every single market. So in the past, we used to see like central inverters for plants starting in 1 megawatt. Nowadays, you can see a 5 megawatt plant built with string phase inverters, right? Three-phase string inverters.
Mm-hmm.
So my point here is that the difference between them is that the string inverters are not using the transformer. So when you have a transformer, you are grounding the one pole of the inverter, and that's what's going to protect you against a PID thing, or you have the chance to avoid PID. On the other hand, if you are using string inverters with a topology that is not ours, you are exposing the modules to the negative bias, and you could develop PID. So, you know, yeah, I've worked with plants with central inverters, and they were using the floating grounding. But, you know, for some reasons, we decided to have the hard grounding, and we did it, and that was possible. But there are plants today, big plants, that are using string inverters, and that will not be able to ground the negative pole because of this reason. So that's my point.
Clear. Another question. How do you figure out if existing system is grounded on the negative or not? Probably, yeah, more the non-engineers here.
Yeah, well, you have to go to the inverter and see how it is, you know, the configuration.
Or ask your EPC.
Yeah, I mean, but the O&M guy should know it. So.
Exactly. Are you working with central inverters, by the way, with your PID recovery boxes?
That is correct.
Okay. Then we go back to Jenya. What does PID look like in an IV curve, in the IV curve data or charts?
Sure. So it's typically decrease in the shunt resistance. So for a single module, it typically looks like initially looks like the fill factor loss. So the sharpness of the IV curve gets more rounded. It gets more rounded, and then after it gets a little more severe, you'll get a step in the IV curve. So if you're doing an IV curve on a string of modules where some have some severe PID degradation, you'll typically see a step in the IV curve where diodes are kicking on.
Okay, I'm just looking at the question. We're kind of running out of time, but I will address a couple more. So you talked about 1500 volt systems. Did you test any 1500? Did you run any 1500 volt test for PID? And is it kind of linear, or what can you say about the differences?
Yeah, so 1500 volts is simply a higher risk for PID. There are certainly modules that don't degrade at 1000 or 1500, and there are modules that degrade at 600 and 1000 and 1500. So it's the higher the voltage, the higher the risk. If you have negative grounding, then you don't have to worry about it, regardless of the voltage. So yeah, there's no real hard and fast rule there. Testing the modules obviously is the only way to really know.
I see. And do you know anything about that correlation? Is it linear from 1000 to 1500 volt? The risk is obviously higher, but how much higher?
I'm not sure if it's linear. There are a lot of variables that contribute to it. Humidity of the site, so site conditions is a big one. So it's just quite varied. The higher the voltage, the higher the humidity. Yeah, if you look at the leakage current of a solar plant in Las Vegas, for example, versus Florida, they'll be quite different, and that will contribute greatly to the risk of the PID degradation happening. So I don't know exactly if it's linear or some other ratio, some other equation, but the risk is increased for sure.
I see. Okay, one or two more questions to Omron. Can the boxes be monitored remotely?
That's a good question. I think that at this point they cannot be monitored, but I should have to double check. Yeah.
Okay. Let me see. What else do we have here? So here's somebody with a string inverter, non-Omron, cannot be negatively grounded. So then the only solution would be to have the PID boxes keep them at the plant. How does that affect? Is there a chance of damaging the modules by reversing the polarity every 24 hours, or how does it affect warranties? Do you work together with module manufacturers there?
Yeah, that's what I mentioned at the beginning, that if you have PID, the first guy looking forward to install the PID recovery box, if you don't have any option, is the module manufacturer, because otherwise the module manufacturer is going to have to change every single motor in the plant. So for sure they are going to say yes, or propose new models, right?
Yeah, exactly. Yeah, repowering is an interesting one. Go ahead, Jenya.
I'll say from a technical perspective, there should be no additional risk by applying a reverse bias in the dark on the modules. Should not degrade modules.
That's very good to know that we have your blessing on that.
Well, we're happy to test it.
Yeah. Yeah. One final question to Jenya. Here's somebody having trouble. When you say PID is not visible to the naked eye, is there an explanation for what looks like arcing between the fingers from the bus bars on the cells of a module?
Oh, I mean, you could have arcing inside of a module. That could just be arcing. So if you have arcing inside of a module, that is not good. That is, you have some either solder joint that has developed a crack and separated and created an actual air gap inside the module, and you're bridging that air gap with an arc, and that's a fire risk. So if you're seeing actual burn marks on a cell, I would call that module end of life.
I see, and we might actually be saving some lives here. Yeah, I want to round off. Yeah, I want to talk a little bit about our upcoming events. We have a solar trade mission in Indonesia with a conference attached, El Futuro Solar in Argentina, Solar Future Nigeria. A lot of exciting places to go, including Tokyo, and of course the big asset management conference North America coming up. We are happy. I can already tell you that we are soon announcing our asset management conference dates for both LATAM and Europe, so please keep an eye on our websites. Yeah, I want to thank both of the speakers, Jenya and Adrián. Both will be at the conference. If you want to get in touch with them, just Google their names. The slides and webinar will be available afterwards. If you can't reach them, you can always drop me an email and I will forward it. If you have any questions with regard to content or our upcoming conference, feel free to get in touch with me directly as well. And as I mentioned, we have a 10% discount with the webinar 20 code on our webpage, assetmanagement.us. Once again, thank you very much, Adrián and Jenya, for this contribution, and looking forward to see you guys in San Francisco next month.
Yeah, absolutely.
Very good.
Thank you very much, Alka, for all your support and the event. Thanks.
Thanks. Have a good night. Have a good day.
Yeah.
And
very good. Thanks, everyone.
Bye bye.
Yep. Bye.
Bye bye.
Bye bye.